Hi, everyone, and welcome to the seventh lecture, where we're going to discuss the polynomial size construction of PCP, a probabilistically checkable proof. And this is often referred to as the low-degree extension PCP or the Reed-Muller PCP, and then you will see soon enough why. Okay, but I want to start before we're showing this construction by quickly remembering what we did last time, and because we again follow this same pattern, the same design pattern. And I think this is another important thing to take from this summer school, which is maybe an advantage that we're doing it in such an intense way, is that there are these design patterns and design paradigms for thinking about algorithm and mathematics and this type of ideas. So hopefully, in addition to absorbing the material, you can see that there are these recurring patterns, and try to apply it to your own research. So last time we talked about the Hadamard PCP, and I didn't have time to give a digest, so I'll do it instead now. So what did we do? We constructed an exponential length PCP with O of one locality for this problem that we called quadratic equation SAT, right? This is an NP complete problem where the goal is we have a set of quadratic equations and we want to know whether we can satisfy, whether there exists an assignment that would make all of these equations, be zero. And this is an NP complete problem, so it means that for any language in NP, we can take the NP witness, encode it using, by adding some exponential redundancy, and then we'll be able to verify the proof using O of one queries. So again, I hear some background noise, so let me try to mute everyone. Okay. Yes. Okay. So that's what we did, and the way to to perceive it is, we started with some proof which is of polynomial length, and we made it something of exponential length. But now instead of reading the whole thing, we can just probe it locally at a constant number of locations. And this is on its own quite a miracle. I mean, we saw it step by step, and it maybe doesn't register something, but this first time that I saw it, I would definitely bet that this object cannot exist. But now we'll see how to take this thing and just make it even more impressive and more otherworldly in a sense. So recall that the PCP that we had two parts. The first part was a Hadamard encoding of some satisfying assignment. So we have this bunch of quadratic equations, and we know that if we give the first variable the value A1, the second variable the value A2, that is a satisfying assignment. And so we took this thing and we encoded it using the Hadamard code, which essentially means take all possible linear combinations of A1 to AN. So it's just taking all possible 2 to the n different linear combinations, or f to the n, and just including them. And we also had a Hadamard encoding of A tensor A, which is just a fancy name for saying, for all combinations of 2 elements. And the idea was, the A1 to AN will let us deal with the linear monomials, and the tensor part would help us deal with the quadratic monomials. So a nice way to think about it is we started with this assignment A, and we encoded it into this huge exponential side proof, which consists of 2 parts, the Hadamard encoding of A. So each point here is some linear combination of A. So, we have any possible linear combination. And here, each term of the second part is a linear combination in quadratic terms. Okay, all nice and well. So we use this, how can we make this magic of O of one query verification? So we really used the linear structure of the Hadamard code in to the limit in some sense. And I want to just take a step back and kind of look exactly where we use this structure and what happened in an abstract way. So first of all, we checked all of the equations at once using a random linear combination. So we said, we have these, like, I don't know, maybe m different equations, and we want to check them. But what we did is, like, we say, well, instead of checking all of them, we can kind of fold them into a single equation. And we did that because it's a bunch of linear equations, so we can take a linear combination of them. And the random linear combination means that there are no, cancellations that can occur with high probability. The second part is that we checked for consistency between the linear and the quadratic terms. And that was an important point because part of the trick is we didn't know how to deal with nonlinear terms, so we just told the prover, well, provide us a variable, provide us all of the quadratic terms, and then we can view them as if they are linear. So we need to check this consistency between this part and this part. That wasn't everything. We also need to know that this is really a Hadamard encoding, and this is really a Hadamard encoding. And the way that we do it is by locally testing the Hadamard code, or in other words, by running the test of linearity. So, each code, each element, each encoding Hadamard A is an evaluation of some linear function. And then what we did is we said, well, if we have from the second lesson, if this is a perfect valid code word of the Hadamard, or this is a perfectly valid evaluation of linear function, then this test will accept. And if it is far from it, then it will reject. So we first checked the encoding, but this only showed us that we are close to a valid code word, that we are close to a linear function, but it didn't, there is nothing preventing. So, if there were a lot of corrupted points, then the test would reject. But if only this point and maybe this point and that point were corrupted, then we have no way of checking that because we're doing it just by probing a small number of coordinates. And this is where we used linearity for the last time. Oh, no, okay. To locally correct. So what we said is, well, we have this, maybe by some annoying chance, I really care about this point, but this point is corrupted. So in order to correct this point, I don't actually read this point, but I can read some random two other points, and using the random two other points, I can use the linearity constraint to correct this code word. So we first tested that we are close to Hadamard, and then after we know that we are in proximity to the Hadamard code word, we can locally correct it, and so we can assume that we actually retrieve the real encoding. So this is what happened in the Hadamard setting. And what we'll do today is to ask, this is amazing that this can be done, but can we do it without adding exponential amount of information, right? Because in some sense, when we're adding exponential amount of information, maybe we can think it's a bit cheating, right? Because we think about polynomial time machines, and it doesn't feel as natural as maintaining the polynomial length proofs that we have in setting, of NP. So it would be extremely, interesting to get it with polynomial lengths, and also, if you think about, these kind of things are actually implemented in practice, and we care about making them linear and as tiny as possible. So if you have an exponential encoding, then this, renders essentially all reasonable application completely intractable. So that's, that's the goal today. And before we actually attack this goal, any questions regarding the scheme or the Hadamard PCP? Okay, so feel free to ask also in the chat if at some point you have a question. So let me kind of tell you what will happen today. Today we'll try to make the encoding from exponential to polynomial, but it would be a bit annoying. So a nice analogy is it could be like you might be on a cold winter night and you have a blanket, and the blanket is a bit short. So, you feel that it's really, really, really cold on your face. So you pull the blanket up but then your feet are really cold. And you say, so you put it down, but then your face is cold again. So this is what will happen today. We'll manage to take the exponential encoding and make it exponentially better. We'll make it a polynomial length encoding, but the whole magic of getting O of one locality will pay for that. And that would make it into a logarithmic locality. So we'll have, polynomial length and logarithmic locality. And what we'll do later is we'll see how we can stretch the blanket and get the best of both worlds by combining these two, different type of constructions that achieve different parameters. So that's the goal. And let's, dive right into it. So the good thing is that we'll deal with the same problem, quadratic equations, and we'll try to employ roughly the same strategy, only now instead of, using the Hadamard code, which is exponential, we'll use the low degree extension code, or the Reed-Muller code, which is much, much, much shorter. So, we have this exponential size PCPs for P. So this is the theorem that we proved yesterday. And we'll reduce it, and today we'll actually prove the following theorem. So the parameters will be exactly the same, except for the polynomial length and the polylog query complexity. And recall that what we'll do is, again, look at the PCP in the setting. So we'll have the proof, the prover. The prover will send proof of poly size. We will make polylog number of queries, which is something, like really tiny with respect to the size of the proof. And then we'll answer. And the proof strategy will mimic what happened yesterday. So we'll start by constructing, instead of a linear PCP, which is a PCP that assumes linear structure, we'll construct a low degree PCP, which is a PCP that assumes low degree polynomial type of structure. So we're just replacing linearity by low degree. And then so we want to construct, we already constructed low degree test, which we did in lecture number 3. And then we'll use it to show that in general, one can take a PCP which assumes low degree, and we'll use the low degree test in order to deduce these polynomial size PCPs. So that's the entire strategy. And let's start with a quick recall of what the Reed-Muller or the low degree extension code is, and also the perspective that would be convenient for us. So, we have a function from Fn to F, and we say that this is a low degree polynomial, well, if its total degree is at most D. Okay, so we have the same diagram, which I copied from yesterday and replaced linear with low degree here. So we have the family of all functions, this is in red, and we have the functions which are of low degree, and we want to, and this would be the structure that we'd like, and we know that we have a test that can distinguish between this part, the green part, and things which are far from being in low degree. Okay, so this subspace of all polynomials of the degree at most D is called the Reed-Muller code. This is just like a name that we call. And again, when I'm saying the Reed-Muller code, it actually says, it's not just a collection of functions, but it's the subspace which you get by evaluating a low degree polynomial on its entire domain. So you take a low degree polynomial, you evaluate it over the entire domain, you get this massive vector, and this is one element in the Reed-Muller code. And together they constitute the Reed-Muller code. Okay, but again, this doesn't really tell us how can we take a message, some bit of like some, let's say, n elements, and we managed to encode them into a polynomial, right? So we had the same thing yesterday with the Hadamard code, where we started with some message and we encoded it by taking the inner product. Now we want to do something with respect to polynomials. Does anyone have a suggestion regarding, suppose I'm giving you, some, think even like a binary n-bit string, how do I encode it into a low degree polynomial? So yes, exactly. Oh, fantastic. So so you have essentially two different suggestions, which are equally good, but and both of them work, but we'll choose one of them out of convenience. So there are two ways. One is that we can use the message to define the coefficient of the low-degree polynomial, which is kind of what we did in the linearity testing. And the other perspective, which again, it's the same, it's kind of like a dual perspective, but it's the one that we use, is that of a low-degree extension. So what is a low-degree extension? It's a way of, taking some function which evaluates to the message and extending it to an entire field. So in some sense, what Morley will do is we'll arrange the message in a green cube, in a cube, it just happened to be drawn in green here, and then we'll kind of consider the polynomial, the unique polynomial of low degree, which take this value on this small cube. So this gives us some formal polynomial, and then we'll evaluate the polynomial wherever we'd like on the entire field, for example. So to make it a bit more formal, we'll fix some subset of f, h for hypercube, and we'll make sure that the size of this hypercube is d plus 1, right? Because we'll think about polynomials of degree d, and we'll think about this h to the n. So d plus 1 values here, d plus 1 values here, d plus 1 on each one of the x's, and then we fill this entire cube. So we filled, a total of d plus 1 to the n elements. This will define a single polynomial of degree at most d, and we'll evaluate this polynomial over the entire field f. So the green cube is h to the m, it's h to the n, it's just the value of the message. And when we look at f to the n, that would be the extension. Okay, so, I hopefully wrote it down. Yes, so exactly what we're doing. So we take this, we embed it in some, arbitrary order in h to the n, and we look at this function, f from h to f, that takes these values, and then we consider a low degree polynomial, consider a polynomial. Notice that I extended the range from h to the n to f to the n, such that two conditions hold. The first one is that the individual degree is at most d, and the second condition is that on the hypercube, on the green hypercube, this polynomial, which takes the same value as the function that we started with. Now, regarding the size of the encoding in the domain, I see the question in the chat, and it is not exponential in the domain. Well, it depends on the setting of parameters, but let me try to convince you in one setting of parameters when it is not exponential. So think about it if you have just, let's say, 3 dimensions, as I've drawn here. So what will happen, and think, so we have 3 dimensions, and think about the degree being proportional to f. So this would incur, a cube, like it would, map n bits into n to the 3rd bits. No, sorry, that would actually incur a linear set. So let me do it sorry for that. So suppose that we're thinking in 3 dimensions. So what I'll do, I'll fix, d, and d plus 1, this is to the 3rd, that would be the total amount of points that we have. And now we choose f to be, I don't know, let's say 10 times the degree. So what we'll actually have here is, so the size of the encoding, so size of encoding, this would be 10d, roughly 10d to the power of 3, right? Which is proportional, which is still linear in the to the 3rd. So if we're looking at a small number of dimensions, then everything would be linear. But we'll actually go slightly above that, and then we'll see exactly the setting of parameters, and it would incur a polynomial blow-up. And I see a question regarding what do I mean by x in, okay. So what do I mean by this? So, So this is this was supposed to be round brackets. So just the numbers from 1 to d plus 1. So I want to take some message in the string from 1 to d plus 1 and encode it. Okay, so that's the low degree extension code. And let's see how we can, so what we'll try to do right now, wait, so Amit is asking regarding the size of the truth table. So just like to quickly say that again, the size of the truth table would be the size of f to the power of the dimensions, right? So it's like the size of the encoding. What is this? This is f to the power of the dimensions, f to the n, right? It's like because we're evaluating the function everywhere, but f is linear in d, the dimension, like the degree of the polynomial, and so it's just like it's the same up to a factor. Okay, but we'll see the exact setting of parameters in 2 slides from now. So maybe it would, we'll do the calculations and maybe it would make it clearer. So, okay. So we want to get this polynomial style PCP, and we want to get it for the exact same problem as we had before, right? So we define this problem of quadratic equation satisfiability, where we have, m polynomials of degree 2, m different quadratic equations, and we want to ask whether there exists some assignment that makes all of these polynomials evaluates to 0 simultaneously. And what we'll do is we'll try to construct a PCP for this problem. And okay, so I shouldn't really waited with the parameters, but okay. So what we'll do is the length of the PCP, it would be f to the power of O log n to the log n. So think about if f is of polynomial of logarithmic size, then this would capture, this would be a linear term. But again, this will happen in a second. So maybe what I want to ask you is for right now, not to focus too much on the parameters, but just to think, let me just like quickly tell what's happening. So completeness and soundness would be as usual. The size of the alphabet would be just the size of our field. The field that we will choose, it would actually be of logarithmic size. And then the length would be this quantity, which with respect to a logarithmic size field would amount to something which is polynomial. We'll have a query complexity, which is polylog, and the total number of randomness would be logarithmic. And I will unpack it in a second, so don't worry about it.
Sorry, one question.
Yes.
Logarithmic on what? So you said the field is going to be
logarithmic in the size of the assignment. So we'll have this, a1 to an, so it would be log n.
Okay.
Thank you. So I want to give you just like the very high level approach of what we do. It would be 3 steps. Each one of them will take, roughly same amount of time. So the first thing is that, again, we'll try to do this reduction. Like we don't have the luxury of solving all m equations. So we'll try to bundle them into one equation. But the point is that whether before with the Hadamard code, like the Hadamard code is because it consists of all linear combinations of the message, it kind of like it's the maximally long linear encoding, right? Because it considers all possible linear combinations. The read model code is also a subspace. So each evaluation that we write, it's also a linear combination, but it is a much shorter one. So in fact, it's just a small subset of the Hadamard code. So we'll have to work a little bit harder in order to bundle them. And then what we'll do, that for every possible equations, this will induce a proof that is satisfied by the low degree extension of the assignment. So what we'll do is, in some sense, we'll take these equations, we'll start with m equations, we'll compress them into one equation, and then we'll kind of we'll take the low degree extension of this equation, and we'll try to solve the low degree extension of this equation by a tool that by now you're well familiar with, which is the soundcheck protocol. what you'll see later how it works. And later we'll add low degree testing to do exactly, to kind of enforce the low degree structure. So it's similar to the structure that we had yesterday. We just need to be a little bit more creative. And there is a question regarding the alphabet size and whether it's bigger than the previous PCP. So yes and no. Like in the previous PCP, we kept the alphabet size, as a parameter. It could work on any field, but indeed it could work with good soundness even for F2. So even if you just like look at 2 elements, and here we'll need a much larger field size, like the minimal size of the field. Yes. Okay. So these 2 main parts that we will go from, and the first one will be to deal with m equations to 1 equations. This is part 1. Part 2 would be how to solve this 1 equation. And part 3 would be how to combine it with low degree testing to make sure that everything is structured properly. So before I start with the first part, any questions? Okay. So, what we want to do is to show that there exists some probabilistic algorithm and think about field size, which is, log or log square, maybe polylog, that would do the following thing. It would use logarithmically many bits, logarithmic in the number of different quadratic equations, and output some quadratic equation, single quadratic equation, such that if there is a satisfying assignment that satisfies all of these polynomials simultaneously, then it would always satisfy this new equation that we created, the bundled equation. And otherwise, if there is no assignment that simultaneously satisfies all of these quadratic equations, then let's say the probability that we'll accept the bundled equation is at most half. This is similar to what we had before, but now we'll be kind of hesitant to use a lot of randomness, and you'll see in a second exactly why. So I anticipate that if I'll ask you now whether you have a suggestion, you start with too good of an idea. So let me start with a completely naive one and then ask you. So the completely naive idea that I would have tried to do in this case is maybe pick 1 equation and just output that equation, right? So you have m different equations, and you want to check if all of them are satisfiable. So sample one of them at random and see what happens. So the point is that this uses very little randomness. You only need log of m bits of randomness in order to do this trick. It's like just to choose. But the soundness error is very, very large, right? Because, if m minus 1 of the equations would be satisfiable by an assignment, but just a single equation will not be satisfiable, then it's just like about sampling. Like if we hit that particular unsatisfied equation, then we'll succeed. Okay, so this is, it's a bad attempt. It's not good enough, but at least it's something which is very efficient in randomness. Now you might ask, why do I suddenly care so much about randomness? Because, and the reason is that the randomness complexity will later translate into the size of the proof, right? Because we said that, if we can always say that if we use a small number, like if we use a limited amount of randomness, then it means that we don't need to write long proofs because these proofs will not be accessed. So the idea is because we are not fine with exponential length anymore and we want everything to be of polynomial length, like logarithmically more efficient, then we'll really try to save on randomness, which in turn will translate to short proof length, which is what we're trying to get. So any second idea of what we can do?
So to connect to your latest comment, so each random correspond to some possible query, if I understand correctly, eventually.
Eventually, yeah. Because, we'll want something important about that, like we'll take these equations and we'll bundle them into a single equation. But then we'll need to kind of like check the assignment, and this would amount later to quiz, yes. Thanks. So any different idea, any thoughts regarding what can we do which is, with better sounds? Like, how can we sample better rather than, just like checking one equation at random? What else can we do?
Taking a linear combination.
Exactly. So SM, Arentia? No.
Yeah, yeah, no, but
Arentia.
I have a question because like M, if you do a linear combination, you need M randomness, right?
Yes.
And now, isn't M a very big number now? It's not a small amount of randomness.
Exactly.
Because our field is super small.
So yeah. So let's see exactly what would be you're absolutely right. What would be so this is essentially what we've done yesterday, right? Like we chose some M field elements and we output this random linear combination. This is exactly what we did with the Hadamard. But this would in turn, something like that would give us an exponential blow, like an exponential size. So what is happening? This really has this small soundness L, like one over F as we had yesterday, but it uses a lot of randomness. How much randomness? We need to choose these M elements, each one of them coming from F. So this is a huge amount of randomness. And if we need to provide a proof for each one of these random cases, then we'll have something which is way not within our limits. So we need to do something else. And this is, oh wow. So I wanted to ask what is the next step, but the next step is already written as a suggestion in the chat. But I want to kind of maybe, and there are several good suggestions. So let me just try to abstract the next idea. So the way I kind of see the next step is, we want to take a random linear combination, but we cannot allow ourselves to choose all this randomness. So a general paradigm that works is using the notion of pseudo-randomness. So what is pseudo-randomness? Maybe, instead of choosing really uniformly at random, let's choose something which uses, some way which is not really random, but shares this nice way, this nice properties of randomness. So for people who are familiar with graph theory, taking a random walk on an expander graph, this is a nice way of obtaining something which looks pseudo-random. But there are also lots of other ways where we can get pseudo-randomness, and one of them is by using algebraic structure. So here is, an idea that was raised by Erkan in the chat, which is, we have this random element R. So it's distributed uniformly at random. So what happens if we also think about R squared? Right? It would be a different number, and think that we are over a finite field. So this is like modular arithmetic. And we can also use R to the third. And all of these numbers, they would kind of be distributed in a pleasing way. And then the hope that these seemingly random combinations would be good enough. So we kind of can get the best of both worlds. So let's try to see how this works. Okay. So
I have a question about this idea too. So
yes.
This A is not fixed. I can easily see that for fixed A, if one of these polynomials is not zero, then after taking linear combination, we'll have non-zero with high probability. But this A is not fixed. So why this sadness error is so small?
So you're talking about idea number 2 here.
Yes.
So this is something which is kind of essentially what we did like in the last lecture. The point is that you can show that if you have like 2 equations, so you want to, you have this like 2 equations, and each one of them you have something which is, and maybe one of them is bad. And now you're saying, instead of checking instead of checking both the first equation and the second one, you add them both up. So now you're saying, well, if both of them are satisfiable, then you have an equation which is equal to 0 and another equation which is equal to 0. So you add them both up and you get something which is equal to 0. However, if one of them is not equal to 0, then at least, morally, you'd expect that when you add them up together, it might also, like the equation would still kind of not be zero. But then you might be a bit suspicious and say, what if it happens to be the case that the first equation would be equal to 5 and the second equation would be equal to -5? So even though both of them are kind of not satisfiable, when you merge them together, then, you know, it would still be a 0. So you want
to... but that works for fixed A, right? We quantify the first probability and then existential over A. So we have to prove that for all A, this linear combination is not 0.
No, but okay. So we are writing like an encoding of this assignment. And now what we're doing is we're saying, well, consider, like, what will happen? When we write things together, we'll get some polynomial of low degree. And then when we want to argue regarding the soundness, then this would really amount into, you know, a simple polynomial identity test. But, you know, let's take this, at the end of the lecture, I'll stay around and then we can just write everything down and I'll try to convince you. Okay. And also regarding the question regarding the sample in the chat regarding the soundness of the first the first idea. So this is just simply because there are m different equations and we choose one of them in front. Okay, so I have to move on. And what we'll do next is, you know, we look at this idea of using pseudo-randomness here. And this idea would use very little randomness because it's exactly as much as we had in idea number 1, which is to choose a single random element. But the problem is that we would require the field size to be really large, right? Because the soundness that we're getting in such a situation would be, you know, the m, which is like the number of equations, over f. And so we'll need the field size to be really huge, which is, again, something that we won't be able to achieve because we want the field size to be something which would be logarithmic in m. So this kind of like, we're a bit in a pickle because we want to implement something which is between idea 3 and idea 2. Like, we want, on the one hand, to maintain small field size, but on the other hand, we also want to have like small number of just like to use very few random elements. So how can we do that? What's the actual solution?
Tom?
Yes.
Is it easy to see why idea 3 works, or are you just skipping it?
Well, the what? Sorry.
The third idea, is it clear why it works, or?
Oh, it's not immediate. Like you have to argue about the pseudo randomness. It can be shown, and in fact we will show it, but for a variant. But it's not immediate. It's just like it turns out that these elements are sufficiently randomly looking. Thank you. Okay, so let's see what we're actually going to do. So we'll start by taking m, the number of linear equations, and we'll identify it with some hypercube. We have this subscript of e just because we'll have another hypercube later, so there is nothing fancy. And we'll choose this subset, this green subset, to be of size which is O of log n, and we'll choose the number of dimensions, which we'll refer to as S, to be log m over log of this. So it will be log m over log m. So why is this horribly confusing setting of parameters? Simply because we want to say that, like, h to he to the power of se, if you just check this equation, then it's exactly m. So what does it mean? We can write, you know, all the numbers between 1 to m in this hypercube, in the green hypercube that we have here. Okay. So now what we'll do is we'll kind of take the first idea of taking, you know, a random element and powering it. But what we'll do instead of like thinking about, you know, a random element of, you know, f to the n, we'll just think about s different elements coming from f, and we'll sort of think about them as a single number, like as different coordinates of the same number. So what do I mean by that? So we'll get the combined equation, what it would be. So what we'll do is we'll write these, we'll multiply these field elements, and each one of them, we will take the power, all of the possible powers that they could take. And by that, we'll manage to bundle all of these polynomials. So if you think in another way, what we're doing is we're considering all of these, like, you know, combinations of these polynomials, and we're weighting them according to like some small number of field elements, which we raise to lots of different powers, right? So it's in some way, it's an interpolation between these two ideas that we saw before. And now let's see what the soundness error in such case. So, you know, obviously if the thing is if the equation is being satisfied, then any combinations of these equations would trivially be satisfied. And the soundness error would be this quantity. And this is coming from, I think you saw it in the other lecture, and if not, you'll see it soon, by the Schwartz-Zippel lemma, which kind of like tells you that, like, you know, polynomial identity testing in this regime is the number of dimensions times the size of the set divided by the field. Okay. And now if we set our parameters, then, you know, we chose s to be log and h to be roughly log. So both of the thing would give us something which is, you know, roughly log m squared over f.
Sorry, what is B sub G1 ... GSE?
It's just the way that we combine the polynomials. So it would be like combining like each polynomial according to, like, you combine the first polynomial according, like, the J1 polynomial according to the R of J1. So this is just the way that we do this, like, multilinear combination of the polynomials.
Mm.
And I think we'll also see that in the next slide, like, so maybe it would give a different perspective. So just to say, the amount of the randomness that we have, what is it? So it's like we're choosing only SE different elements from F. So it's F to the power of SE. Whoops. And what is F to the SE? So if F is proportional to HE, then this would give us something which is polynomial, right? So, like, F, we chose it to be, so what we have is we chose F to be polylog M, and this would be to the power of log M to the log M. And the nice thing is that this amounts to something which is polynomial in M. So that's the kind of like the way of doing this pseudo-random combination of linear equations. And what we'll do next is to combine, to assume that we combine the equations, and now try to construct a low-degree PCP for them. So let me try to kind of like illustrate the following setting. So what we want to do is we have this verifier, and the verifier is giving getting this, you know, single quadratic equation, and we want to know whether there exists some proof, some assignment A that would satisfy this polynomial. Right. So think about just a low-degree polynomial that gets some encoding of a satisfying assignment for for a single quadratic equation. So the challenge in some sense is that the polynomial could depend, you know, in each one of the variables, and we don't want to query everything. So the idea would be to use the trick that has been used in quite a lot, like the fundamental tool that we used a lot in interactive proofs, and somehow make it work in the PCP setting. Okay, so let me kind of like remind you. So sum check tells us something nice. If we're looking at a problem that can be expressed as checking that some, low degree polynomial is equal to 0 in a certain cube, like if we have, a cube and we want to know that the sum of the elements in this cube is 0, then we have this amazingly efficient sum check protocol. So, right, like think about, like the idea is that we want to make, to define a polynomial such that if the assignment is being satisfied, then the sum of the elements in the green cube would be 0, and otherwise it would be non-zero. And then this is just an instance of the sum check protocol that we've covered in the A lectures. So my goal at the moment is to write down a polynomial, some equation, some arithmetic equation that would be satisfiable if and only if there exists such such an assignment. So let's see, what can we do? So think about any possible assignment where we give each variable from 1 to n a value in f. So what can we say in such a situation? Like when we apply the polynomial to the assignment, then this is essentially, this is a quadratic polynomial, it's a quadratic equation. So we're just like summing over all of the monomials here, and we're adding, and we're giving, and we have some coefficient times the variable. And then what we can do is we can take the low degree extension of this function. So instead of like considering the function here from n to f, we can extend it into a polynomial. And then we'll have, the low degree extension of c, which is a function which, on these values here, it would be exactly as this coefficient c of ij, but we can also evaluate them over the entire field because it's a formal polynomial and we can evaluate wherever we want. And same thing with respect to alpha, with respect to the assignment A. Instead of looking at A, we'll encode A using we will take the low degree extension of A, so it will be some polynomial where the first, if you query it onto this cube, you'll get the value of the assignment A, but you can also evaluate everywhere else. Okay? So, and exactly like this A and C, this is just like the low degree extensions of, this A and C. Good. And now, what can we say? So we have this addend that we'll kind of denote by Q. It's a function of some variables y and some variables z of this form. So this is a bit confusing, so let me try to unpack it. So the moment that we went from here to here, something kind of, maybe it's even better just to see it with the AIs because you don't have this additional notation. We took a vector, like something which is just like, just a vector of values, and then we embedded it in a cube. And then we took the low degree extension. So there are two things that following. So first of all, even just to represent like the vector A, which is just, a bunch of A1, A2, up to AN. So we first fold it into a function in S variables, just because we want to take this vector and somehow arbitrarily put the values inside the cube, right? So think about it, if the cube was two-dimensional, it would be just rearranging A1 into AN into a matrix. But now we do it in more direction. And regarding the question of why we're taking the low degree extension, you'll see in a minute, this is all because this is what the sum check protocol requires. So the point is that we have this nice way of verifying the sum of a cube, but we can't verify in sublinear time, like in sublinear resources, the values of like the sum of any cube. We can only do it if we're allowed to see the low degree extension of the cube. That's what the sum check protocol gives us. Okay, So when we're looking at this term that we get, which will denote the function q, we get this function of individual degree, which is it's twice the size of hv. And to see that, what's happening is that you just count each one of these values, how many points you have to fix. So you have to fix these endpoints here and endpoints here and endpoints here. And so in each of the s variables that we'll have, that would be the degree. And when we take the whole thing, it's like the total amount of points we have is n to the sv. So it's a bit confusing, but you get used to it after a while, because it's just this setting of parameters of taking just a vector and compressing it into something which is log n over log n dimensional cube. And essentially, this is a standard way of taking the problem of, so what have we done here? We reduce the problem of checking an equation into checking this sum. And notice that this q is indeed a low-degree polynomial. It's a low-degree extension of information. And this is exactly what we can solve using the sum check protocol. Okay, so let's see how this works, and hopefully this will also clarify the protocol a bit. So, suppose that we have a satisfying assignment A. So it means that when will the polynomial p be equal to 0? So it would be equal to 0 if and only if this summation over the hypercube would also be equal, because we arithmetize it, we chosen this polynomial such that like p is 0 if and only if this happens, right? And maybe like a good reminder to see that is because it's just like, oops, okay, not, wait, sorry. Because this q polynomial that we defined is just this low-degree extension of p of a. So if we evaluate it over this hypercube, like the hypercube which we later extended, then we get exactly the same as p of a. So p of a is equal to 0 if and only if the sum over the cube is equal to 0 for this low-degree extension. And then what we want to do is just like to do this probabilistic check of the arithmetized statement. So what I mean by that, I want to apply the sum check protocol. But here we have a problem, right? The sum check protocol, it's an interactive proof, and we want to write a PCP. So what can we do? So let me kind of like give you the hint, and I'll also skim later all of the questions in the chat. So apologies, let me just like finish this idea. So the point is that I want to run the sum check claim, but I don't have a prover to interact with. So what I'll do is just the simplest emulation where the prover is kind of writing down the entire, like possible tree of interaction that we can have with respect to the prover for sum check. And then we are in a good situation. So the prover provides us with two things. It provides the low-degree extension of the input, this A hat, the low-degree extension of the satisfying assignment, and the entire truth table that I need in order to emulate the sum check protocol. And then, I have this inside the PCP verifier, we will emulate the interactive proof sum check verifier. So this is a verifier, it gets like this field F, some domain H, number of variables, and some claimed sum, which is 0. And, we'll do all of this interaction in our heads, right? And because like there is no prover to interact with, but rather, I'll run this verifier, and the verifier would send a message to the prover, and then we kind of like look at the truth table of the prover and see, well, if the truth table got the message out, then it would send us these values, and so we'll query that proof and that proof and that proof. And we'll do this thing using some, some random values that we will choose. And finally, what we'll do is, if you remember, at the end of the soundcheck protocol, we need to evaluate the polynomial at a single location. Just like to remind you from the A lectures, what soundcheck gives us is that if I want to check that this polynomial is equal to 0, it reduces it into the problem of evaluating this polynomial Q at a single random point. And so we want to evaluate this at a single random point. And, the C, this is the low degree extension of the coefficients. So we can just do it locally without any queries. And all we have to do with respect to the PCP oracle, which is a low degree extension of A, is to query it at the random locations that we need for the soundcheck protocol. So that's the idea of what is happening there. So this is the queries that we will make to the oracle. And now if you want to look at the query complexity, well, what are we doing here? The query complexity, we look at the soundcheck protocol. So we'll need at each point to read a proof, which is of this length. And because we are, working of roughly an order of SB elements, then it means that we'll have to do it for S many rounds, or 2S many rounds in this case, because it's two variables. So the total would be O flog squared number of elements. And we'll query these two elements that we need from A hat. One for this variable and one for the other one. And in terms of the proof length, then, well, the total amount of that we'll have is the Reed-Muller encoding, the low degree extension of the assignment, which is just F to the SP. And we'll also have to write all of these values, where this is where we write the all the possible random choices that the verifier made. So this corresponds to all of the R's that we're sending times the description length of each one of these messages. So this is exactly why we want to really be careful with our randomness, because we have to later provide proof for each possible conversation that the prover and verifier might have in the soundcheck protocol regarding that. Okay, and in our setting of parameters, when we choose F to be polylog n, this would just amount to having a polynomial length. Okay, and completeness, well, it's trivial because if this is a satisfiable assignment, then and this is so if this is a low degree extension of a satisfiable assignment, and that's the actual prover strategy, honest prover strategy, then by definition, there exists this thing that exists equals to 0, and we're running this interactive protocol that is consistent, and so the IP would rule correctly, and we will rule the same. And in terms of soundness, well, if it is unsatisfiable, then if we assume low degree structure, so if we now say that the prover really sent here a low degree extension, and this is why this is a low degree PCP, because we're taking for granted for a second that it must send a low degree extension, then by the validity, by the soundness analysis of the soundcheck protocol, we'll get this soundness, which is just again the dimensionality times degree over the size of the field, and that's essentially what we want. Okay, so that's the analysis of the low degree PCP, and let me look at some of the questions in the chat. So the complexity for computing this PCP is indeed exponential. This is not a doubly efficient proof system. The prover, we think about it as computationally unbounded, and it needs to make a whole lot of work. I see that Philip answered Amit, and regarding the if and only if, that's a good question by Tal. So I think it is actually a subtle question. So definitely, so let me see if I can convince myself. So if the assignment is 0, right? Then by the choice, because this is a low degree extension of that, then this must be 0. So that we know. But now we're saying if this sum happens to be 0, could it be the case that this assignment might not be 0? And yes, so it doesn't have to. So let me kind of say, so what can happen? What could possibly happen is maybe that because we're summing over a finite field, like the number would definitely, like, so what will happen is that if this is not as satisfying, like if this is equal to 0, there are two ways in which it could be equal to 0. Either because it is 0 all the time, or because we'll have cancellations. But the way that we chose our Q is like, the only way this could happen is if we're kind of like adding things together as and capping the number. So maybe a good way to think about it in a simpler setting. Let me try to kind of like write it in a simpler condition. So suppose that you have this like 3-sat formula. So you have that, I don't know, like clause 1 and clause 2 and clause 3 and so on and so forth. And then you can like write this low degree extension, which would give you an indicator of whether each CI is being satisfied. So it could be the case that, so like this sum would be the number of satisfiable assignments. So if you're working over a finite field, and which is small, then it could be the case that you're kind of like, you might sum and somehow reach 0 by another way. But in our setting of parameters, this inherently cannot happen. And again, if this is not clear, I'd be happy to stick after the lecture and like show it explicitly. For our case, I just like tight on time today. So let me continue with the low degree PCP. So what we want to do now is to kind of put these two parts that we have together. So how do we do that? We consider the following protocol. So in this protocol, we have a prover, and the prover sees all of these equations, and it has some satisfying assignment, whereas the verifier only has the quadratic equations. Okay, nice and well. So what we'll do now is that, we'll go over every element in the larger cube, and we'll say, this is, we'll define this P of R, which is what happens if we take this bundling algorithm, right? And we say, this is take this polynomial and this polynomial and this one and this polynomial and bundle them together according R. And we'll do it for each one of the choices of the R. So this is why, we wanted to be efficient in randomness, because you don't like want to go over too many R's, because we'll have to write something for that. And then we'll consider the evaluation table of the sum-check protocol with respect to that choice of randomness. And, we'll write the whole thing, and we'll send to the verifier the PCP, which consists of this entire evaluation of this, whole sum-check strategy. So we think about this as this like pi of sum-check. This is the part of the proof that would help us emulate the sum-check protocol. And also we'll take just the Reed-Muller encoding, the low degree extension of this satisfying assignment, and send it as well. Okay, now the verifier will take this random R and get the same equation, the same bundled equation with respect to this R. And now we'll run sum check to verify this condition, which would amount to the satisfiability of this equation. And we'll do it by emulating sum check. And how will we emulate sum check? So we'll do it in our head, and whenever we try to communicate with the prover, we'll go here and here and here to get the answers that the prover would tell us. So that's the exact protocol. And completeness and soundness will follow as in the standard setting, because if this is justifiable, then for every random choice, the combination would be satisfiable, and so the sum check will hold. And if we are not satisfiable, then, except for the soundness error that we get from the like sum check protocol erring, then so is so if it is unsatisfiable, then except from the error that we get from the bundling, we know that the bundle function will also be unsatisfiable. I mean, if we bundle in the wrong randomness, then this is like, but it only happens with a very low probability. And then in addition to that, so this would mean that like doesn't matter what low degree extension we get, this would still be unsatisfiable, and then this reduces to the soundness of the sum check protocol. So we get like this term from the bundling from part 1, and this term from the sum check protocol, and we just run the two things. Okay, so that's that. And now we are kind of like, we need to deal with the last thing, which who promised us that the prover actually sent us this low degree extension. Because in the real world, the prover can send here anything that she or he would like. Okay, so recall what we had in the low degree testing lecture. We kind of said that we have this, some query algorithm, some probabilistic Oracle machine that gets query access to this function f. And if the function has, a certain degree, then a degree at most d, then it always accepts. And if it is, let's say 1/10 follow from all of the functions that have degree at most d, then this thing will accept with probability, which is at most half. And also this low degree test, if you remember, it was just like query a random line in the cube. So it's also something that you can make efficiently using this many queries, which now setting of parameters because f is logarithmic. So it would be just a logarithmic number of queries. And okay, so I think the total degree is not really important, so we can maybe ignore this remark. But so having remembered the low degree test, let's see how the PCP would look like in the general setting. So how would we show this theorem? The idea would be as follows. We'll take the exact protocol that we had before, which we're happy with. And in addition to that, we'll want to run a low degree test on pi of a, on this element. So we want to check that this is really the low degree extension of a. Now, again, we'll have the situation that the test, because it's a proximity test, we'll know that if it's fine, and if like this is a valid encoding, it's a valid low degree extension, we will accept it as probability 1. However, if it's not, then we'll only be able to reject it if it's like 1/10 far. So after passing this test, we know that either we are we have the right value, or either this is like a perfect thing, or it is something which is close to a low degree extension. So okay, so there is like a small remark here regarding individual degree versus total degree. And in some sense, we described, so there are two things that one can do. Like we described this protocol in terms of an individual degree extension, and the proof that we had was total degree. Then either one, derives the individual degree from the total degree, or also it just increases the sum SL by a small factor. So this is, just an aside, it's not an important point. And the more important point is what happens if, we said that if the low degree extension is far from low degree, then we'll reject with high probability. But if we are close, then in fact, as opposed to what happened with the Hadamard setting, where we really needed self-corrections, here we can, like the two queries that we have happen completely in random, so we can, just pay union bound over these things. But alternatively, we can just draw a random line and correct the point by interpolating the value as a random line. So just to say that there are two approaches that you can take. Okay, so just like to make a digest of what happens. So we have the following things. So we show this polynomial length PCP with polylog locality for quadratic equations. And that this was a PCP that was based on the Reed-Muller encoding. So we essentially took an assignment and encoded it into this low degree extension. And we used the structure of the Reed-Muller code to first, reduce these M equations into one equation using the pseudo-random linear combinations. We checked an equation using the soundcheck protocol, which means that we also had to send, the truth table of prover for soundcheck. And finally, we used the local testability of the Reed-Muller encoding using low degree testing. So this is kind of analogously to what we had with the Hadamard PCP, only things were a bit more constrained. So at this point, I'll stop the recording